Okay, so our upcoming events for the ACM. So next Monday, we have from rapid model development to faster production deployment, best practices in data science, Zeppel. So if you're familiar with using Jupyter Notebooks or Jupyter Lab, it's another environment like that, although Zeppel is much more multilingual, so supporting R and other languages as well. So I ran into those people at, what was it, one of the earlier summits on cloud computing. It was the rework deep learning conference in January. So next, squeezing down computing requirements of deep neural networks, speaker from UC Berkeley. Then we've got a series on state of AI and ML. That's a repeating series of training events. So this is, so we've got valleyml.ai. So they're teaching a series of courses. So you can check them out through a web search. So state of AI and ML, search for valleyml.ai. Our next evening talk is emergence of RISC-V, computing architecture, embedded apps, and machine learning acceleration. And then major applications of AI in healthcare. Then there's machine learning and deep learning boot camp. So this is our Saturday event that we've got coming up. So we have a call for volunteers. We have about a dozen volunteers that meet once a month over dinner. So if you want to be one of our volunteers, we'll buy you dinner then as well. And that's where we talk about planning upcoming speakers, if we're giving training seminars. Other times we plan on working with the science fair. We do science fair judging in March. So we don't do just evening talks and training, but we also do STEM support. Some of the membership services can be simple as show up a bit early and help with the registration desk, or if you want to get into working with Salesforce, if you have some experience with Salesforce.com to help manage our membership database, we have some interest in that. So we would work with Salesforce on a nonprofit basis. We also need some help with our BitDropper editing, so we can provide the content of our upcoming talks on a regular basis, but BitDropper is a print newsletter that we mail out to people that opt in for that. We have an upcoming deep learning class, so we are looking for PDS teacher aides just to increase the student-teacher ratio. So we've got people developing the Jupyter Notebooks and having the cloud. We just want some other people to walk around the classroom and offer some support. So we're doing our next class will be on PyTorch and transfer learning. That'll be in about 2 months. So if you're a TA or teaching assistant, then you can also get into the class for free. And it's a 8-hour class on a Saturday, including lunch and coffee breaks. We always have a call for speakers out for either the general computing or the data science. So note to the speaker and also to the audience, the recording is for our YouTube channel. The microphones will just pick up what the speaker says. It won't pick up anything the audience says. So if I ask that the audience keep their questions down to 30 seconds and then let the speaker answer. Because I'm asking the speaker to try and repeat all the questions for the recording for future YouTube viewing. So that way they don't just hear some random answer and they have no idea what the question is. Also, hint, hint, don't ask a 3-minute question. We have to be nice to our speaker. He has to be able to repeat it. We want to be nice to our speaker.
Sure.
Also, any announcements from the floor where there's some microphones available? I'll go from one side of the room to the other. So announcements you might make is, hey, my company's hiring some data scientists. Or did you hear about this other meetup or conference in the Bay Area? So I'll go to one side of the room, raise your hand if you have any announcements you'd like to make. Any interesting events to talk about? So I'm going to the KDD Data Mining Conference in Anchorage, Alaska. That'll be August 4th to 8th. So last year it was in London, so that should be very good. It'll probably have 2,700 data scientists in that, and it's half industry, half academic.
Thanks.
So raise your hand. Any announcements? Other meetups you like? Yep, go ahead. There's a microphone coming by.
Just one conference called Encore will be held in our palace in San Francisco at September the 15th
Okay, CUDA dealing with NVIDIA type of things?
Actually dealing with how we commercialize the open source projects. So
Oh, for specific
if
open
you are
source.
doing open source, it should be a good opportunity to get good one, finalize one.
Okay, what's a URL or search term again?
It's for open core.
Open core.
SCORE.
Oh.
Open core.
Okay, thank you. So other questions or comments? Okay. So I'm mostly caught up on my data science hiring. I'm hiring 5 people between here in Sunnyvale and Pune. We have a Internet of Things company, and I run a data science group growing from 9 to 14. So I made an offer to one person last week. I'm looking for people that have deployed at least 3 data mining models, doing general prediction, clustering, unsupervised learning, and deep learning. Tonight's speaker is going to be talking about inside the black box. How does a neural net understand names? So it's all around named entity recognition. So it's used in natural language processing, or NLP, chatbots, customer relationship management, or CRM. They're going to present their latest research on NER using architectures like LSTM, long short-term memory. That's a type of recurrent net. The memory state helps you remember over time. That's the longer-term memory part by having the memory units. Used for sequence tagging, they're using conditional random fields, or CRF, and word embeddings. So word embeddings would be where you, instead of using a bag of words of 50,000 binary inputs, you might have 300 continuous numbers going in to represent a word or concept. They'll be looking at neural activation values and different conditions. They'll provide real-life examples on how they're applying it to 10 languages, including the list that's up there. We'll be looking at accuracy, speed, and memory footprint, compare best-known deep learning architectures, and focus on interpretation of the network. So interpretation is really interesting for a lot of fields in order to gain trust of the client. So that's always very important. A little bit about our speaker. Dr. Kfir is Chief Scientist of Basis Technology of the Text Analytics team. So 18 years working in natural language processing, statistical machine translation, machine learning, ontologies, language generation. The CTO of IntuView in 2005, supporting national security and counterterrorism missions by deducting authorship, sentiment, intent, and other contextual information. He co-founded Comprendi in 2013 that transforms big data into actionable marketing insights. He teaches courses in computer science, digital humanities, machine translation, algorithms, and NLP at 3 different universities in Israel. He received his PhD in computer science in Tel Aviv University on semantics and machine translation. So please help me give a warm applause for Kfir.
Thank you. Thanks so much.
Oh, thank you.
Okay.
So he can eject. I know. That's what I was just saying.
Hi, everyone. Give me a minute just to share my screen here. So do I need to use the mic?
Yeah, there's one for the recording, correct?
Yeah, the recording is right here.
Oh,
And there's another one, right? So
yeah, the other one is for the loudness, just so we can hear you in the room.
okay. Oh.
Oh, and please silence your phones.
Okay. Can everyone hear me? There is echo there or something. Will be.
That's the question. So if we no more echo.
Test 1, 2, 3. Yeah, works well. Okay, So, hello everyone. I'm Kfir. I'm the chief scientist at Basis Technology. I'm very happy to be here. Thank you so much for coming. Tonight I will talk about how does a neural network understand names. I will focus specifically on named entity recognition, which is probably one of the most common and important tasks related to natural language processing, NLP. And I'll give some background first, and then I will show you what types of networks we use to kind of solve this problem. I'll show some results, and then I'll talk about some other stuff if we have more time. So please ask me any questions, or happy to get into discussions too. Okay, so let's start. So this, just a general description of what is named entity recognition, or NER. It's about finding names of people, organizations, locations, and some other types. And just plain running text written in many languages. So we're focusing on many different languages at Basis. Let me give you an example. According to Elon Musk, Mars rocket will fly short flights next year. I think he said that 3 years ago. But anyway, Elon Musk is highlighted in blue there, right? So this is a person entity, and Mars is our location, and let's say, and next year is a time expression or a date entity, if you like. So maybe some of you will think that this is a simple task, right? Maybe we could just compile a list of location names, let's say, right, from Wikipedia or something, and then use a very simple lookup procedure to find all the instances of that list in the text, and that's it. But then we don't know whether Mars was mentioned as the location or the candy bar, right? So that's a problem. We need the context to help us resolve this kind of lexical ambiguities. So the context is definitely important, and let's do this fun exercise. I'm sure many of you know that, but anyway, to those who don't, so this is the checker shadow illusion by Edward Edelson from MIT. So look at this board and tell me, or raising your hand, if you think that the background of the square represented by B and the square represented by A, their background colors is the same. Yeah, so probably many of you think that it's actually lighter, right, than A, but in fact it gets darker by the shadow that is dropped there by this green element, and it gets to exactly the same color. And it's the context surrounding B that makes us believe, that B is a light box in this board, and therefore it has to be, lighter than A, right? So it's the context that matters here. And if you don't believe me, just cover everything else. You will see it immediately. I didn't play with the colors. I can promise you that. Okay, so anyway, context is important, and also for human languages, of course. You can check out this sentence. Can't play Spain, improve your playing via easy step-by-step video lessons. So Spain is an entity here, but it's not really a location, right? So what is it? Do you know? Yeah, exactly. So this guy wrote this jazz standard, right? Spain, Chicoria. Or check out this sentence. Mom is a great TV show. So mom is, typically, we use mom to refer to this word mother, right? Like maybe 99% of the time. I invented this number, but probably something like that. But in some cases, we use it to refer to this American sitcom. I don't know if you're familiar with it, but maybe you will find it during airing time of this show on Twitter or something. You'll find some mentions of mom referring to this TV show. Okay, so it's more tricky than what we think, right, at the beginning. Now, named entity recognition is probably one of the most important tasks in NLP, especially if we're talking about, information retrieval, right? So it all begins with a document, and then we start collecting some information from the document. And in many cases, it begins with extracting names of people, organizations, locations. And then we start to look for relationships between those entities. And sometimes the sentiment that is expressed toward those entities, by the author of the document. Maybe events that those entities are mentioned in. And some other types of information that we extract from the document. But everything begins with those entities. And so it's kind of like, if you want, the backbone of the document, right? All these, the list of entities. Anyway, so I hope I convinced you that it's important and it's not so easy to solve it. So now let's talk about how we actually address this problem from a machine learning perspective. So let's first, model the problem. Named entity recognition is a sequence labeling problem. It means that we process word after word. Okay, so we have like a sequence of words. So we break the text into words and then we process every word. And then for every word, we try to assign a specific label. But keep in mind that names may span across multiple words. So we have two types of labels per entity type. For example, we have B pair, beginning of a person entity, for the first word of an entity person type. And then we have I pair for the following words, second word, third word, and so on. We have similarly B lock, I lock, and so on, right? We also have other that will, or O, for words that are not names. So you can see this example. I'm working for basis technology, so I'm working for the get O because they're not names, and then basis technology, so we have B org and I org, right? Beginning of organization and so on. This is also called the IOB annotation scheme, inside, outside, begin. And this is the kind of, this is how we expect to see annotated data, right? Exactly like what you see right here. There are some extensions to this annotation scheme, but I think for the sake of this discussion, it's good enough. So at Basis, we use multiple engines to address this problem. And each engine takes a different algorithmic approach, I will say. And then we collect the results coming from those engines and send them to this decision-making component for generating the final output. Now, probably the most important engine is the AI-based engine. We're going to focus on this engine. It's just a machine learning algorithm, right, that we train using some supervised data, some examples. But these types of algorithms, they're pretty accurate, but they're not 100% accurate. So they tend to fail on those special cases for which you don't have enough examples in your data set. And this is why we combine the other engines that take a more deterministic approach to the problem, like dictionaries, right? And rule-based engine is just using regular expressions. And our clients can also edit those dictionaries and those rules. So they add more flexibility to the whole process. Okay, so we'll focus on the machine learning engine, and let's briefly discuss the difference between traditional machine learning and deep learning for NLP. And I put here an example from a different task. This is, let's say, sentiment analysis, but it doesn't really matter, right? Because NLP starts from, and the input will be text, and then the output, single label, a collection of labels, and even text, right? In machine translation, for example. So here is just we have a text right there, input, and then with traditional machine learning, we start with feature extraction, right? So we extract features from the text. We begin by breaking the text into words. Now, if you think English, so that will be straightforward, right? To break text into words. But Chinese, for example, or Korean or Japanese, right? Where there are no spaces between words, that would be more challenging. Once you get those, the words, you can look at linguistic features like part of speech tags, right? So nouns, verbs. It will help you to resolve some lexical ambiguities. Like if you take the word book, right, could be noun or verb, right, with different meaning. And then we have lemmas. So a lemma is a base form of a word without all these prefixes and suffixes. And it's very efficient if you're working with a highly inflected language like Arabic, for example, Hebrew, Spanish, Russian, these languages. Anyway, there are many more features. It's pretty interesting, but I'm not going to go into more details there. But we get all these features and we vectorize everything. We put everything in a long vector, right? A mathematical vector, and we just use that as an input for traditional machine learning, yes.
Are the vectors all the same length?
Depends, but yes, I mean, you have, mostly you have, yeah. So the question was if the vector is of the same length. But in most cases, yes. Okay, so with deep learning, we don't use this feature extraction step. We go directly from text to a mathematical representation. And we do that using word embeddings that you mentioned before. I will say a few words about word embeddings in the following slides, but for now, we do break the text into words. We work on the word level, although we can also work on the character level. But then we have a vector for every word, a fixed size vector, let's say 300 dimensions, that we can create ahead of time. Okay, so we pre-train the model that generates these vectors. And those vectors will represent the meaning of the words, right? In the sense of like two words that have similar meaning will also have similar vectors in a mathematical perspective, right? Using cosine similarity or any other mathematical distance function.
So just to clarify also, these vectors in essence are kind of looked up from a dictionary.
Yes, exactly. The vectors exist in a repository, right? And something like that. And we can just search for these vectors and put them together and you have a mathematical representation. We don't really know how to interpret these vectors. It's just a sequence of numbers. Anyway, we'll get into more details very soon. Now we take all these vectors and we send them to a deep learning model, to a deep neural net, different architectures, configurations, whatever, and that's it. That's straightforward, right? So if I'm a traditional machine learning engineer, I'll focus mostly on the feature extraction part. Many of our engineers at Basis, they do that. So they try to find specific features that work on every language, on specific languages. So we have people who speak all these languages. We support about 40 different languages, okay? So that's pretty difficult. And those tools, lemmatizers, part of speech taggers, are very sophisticated tools. They by themselves are based on machine learning algorithms. And if I'm a deep learning engineer, that's easier. So I need to just play with TensorFlow, right? With different configurations and try to find the best architecture that works. And if it works for English, it may work just as good or almost as good for other, at least Latin-based languages. And that's pretty cool. I mean, for us at Basis, it means that deep learning is a much more generic approach for NLP. So this is why we're exploring this direction. Okay, so neural nets, that's what we're going to focus in this specific session. Let me give you some definitions so we can all we'll be on the same page. So for the sake of this discussion, a neural net is just a vector transformation component, I say. So you take this vector x as input, you send it into this vector transformation, and then you get a new vector h, which is the transformed version of x. Okay, and this transformation has some parameters inside that we can adjust. We can adjust those parameters, and we do that during training, right? Because training is just a collection of pairs of these vectors, x and h, and we adjust those parameters so that for every x that we're going to send in, we get the correct h that we want. Not just the x that exists in this collection, right? But every x. So that's training, basically, like every machine learning algorithm that you're familiar with. Now, the most common transformation is just a linear transformation, right? This is a linear transformation. It means that this W is actually a matrix. X, we said it's a vector, so we get here a vector, it's matrix multiplication. and then we add another vector, which is another parameter to the transformation, to the model, and this is like the bias vector, right? It doesn't depend on the input vector. And we get a new vector. This is the linearly transformed vector, and then we send it also to another function, a non-linear function typically, right, element-wise. And we get a new vector, and this non-linear function is needed, especially if you do this kind of things, right? So you can take this output vector and send it as an input to another transformation. That's a deep neural network now. So we're using two transformation, one after another, and you can see it right here, right? Because we have like two sets of parameters. It's not the same, W right here. So W1, W2, B1, B2. And you can see it right here why you needed this nonlinear transformation, right? Because if you didn't have this, so W2 and W1 would collapse, and then you get like a linear transformation. Yes, please.
How do you choose W1 and W2?
So the question is how we choose W1 and W2. So again, those parameters, they start randomly, right? So you initialize them randomly, and then you start modifying these parameters during training, right? And there are algorithms to do that, like backpropagation, right? All these algorithms. And this is exactly what they do. They adjust those parameters, W1, W2, all these parameters during that time. Okay, so we have this. We know, so it's important for the next slides very soon. I'll show you how we use RNNs and LSTMs. Okay, I promised to talk about word embeddings. Let's do that now. So as we said, we have a vector per word. Now, I'll say a few words about transfer learning later, where we talk about contextualized embeddings too. Okay, so but for now, it's just a single word per, a single vector per word. So let's take as an example car and truck. Okay, so we start, the way that we create these vectors is by looking at a large collection of documents, just plain text, no annotations are needed. And then you start with a random vector basically. So this is just a random vector, let's say for car, and random vector for truck. And the way that and then we're gonna modify these vectors. And the way to do this is by looking at all instances of the word car, all the mentions of the word car. And we look at its vector. Let's say this is the vector representing car, initialized randomly. And we modify this vector to maximize this dot product. And this dot product is with vectors of words that exist in the near environment of car, right? The surrounding context, we call it. So we modify C to maximize this probability. And there is a model to do that. And I'm just giving you the intuition, right? And here too. So for the word truck, we have a different vector, and we also do the same for truck. So it means that if T and C, or car and truck, will have similar words, kind of similar words in the near environment of those words, in all the mentions of those words in the collection, they will be similar in the sense of dot product. And dot product is almost cosine similarity. So that's exactly what we're looking for. And after many iterations, you get to a point where you have stable vectors, and you can do things like that. You can take the vector of the word Japan, and then subtract the vector of the word Tokyo, and then add the vector of Berlin, and you get a new vector. This vector you just created, this vector is not part of your vocabulary at all, right? But if you check and you run cosine similarity or dot product of this vector with all the vectors that you have in your vocabulary, this could be a lot, you will see that it will be mostly similar to the vector of Germany. Okay, so it works pretty nicely, right? Because you took a country, subtract the capital city, added another capital city, and you got their regional country back. That's pretty cool. And this is the kind of calculations, if you like, that happen inside a neural network. You start by representing the text with embeddings. You send them into that neural net with, that does all these calculations. Additions, multiplications, nonlinear functions, and so on. And eventually we get the prediction. Yes?
nearness, for example, if you look at the last thing, we talk about driving. In German, especially, you don't want to have drive on the very end of the sentence, and potentially, as opposed to being contextually near it. How do you go on to determine nearness inside your system?
Specifically for embedding, so there are different techniques to do that. The simple word-to-vec, published first by Google, doesn't take into account long-distance dependencies. But there are other techniques. For example, there's a nice work that they use dependency parsing first. So they parse this. The question was about how do you take long-distance dependencies between words and not just the words that exist in the near environment, right? That was the question. So I just said, there are works that try different techniques to capture that information. One of them is by running first dependency parsing on the sentence, and then work on the dependency tree, okay? And then you can take that into account if you like. So it's a very interesting work, so you can check it out. Yeah.
How do you, if you have an out of vocabulary word, so what are the guidelines that you follow for creating that new vector for the embedding, because you have to initialize with some kind of numbers?
Right, so the question is about what do we do with out of vocabulary words, right? Words that we don't have vectors for. So I'll get to that. I have at least 2 slides about this very soon, but the hint is that we're using character-based prediction, and we kind of combined word-based and character-based. So basically we represent words with character-based embeddings. I will show it very soon. Okay, I think we're ready to start talking about architectures for solving named entity recognition. So this is the first attempt, published in 2011, the first attempt to do named entity recognition using a neural network. And remember, we said that we process word after word. That's a sequence labeling problem. So let's say we process this word now, and we try to predict the label for this word in focus right here, Spain. And this is part of the sentence, okay? So you can see the near environment of this word that we want to predict the label for. Okay, so what we do, we take the vector of Spain. We know how to calculate these vectors ahead of time. We do that. We have the vectors. We take the vector here. If we don't have the vectors, we'll get to that very soon. So we take the vector here, and we also, in order to capture the context, we said context is important. So in this case, we simply take 2 words before and 2 words after. We take their vectors. So let's say each one of these vectors has 300 dimensions. So we put them one next to each other, we concatenate the vectors, and we get a long vector, 1500 dimensions. We send it into a linear layer, vector transformation, exactly what we said before, and another transformation, and maybe another one. And eventually the output layer right here is of the size of the number of labels that we have in our data set. So if we're working on a classic PLO problem, people, location, organization, we're going to have 7 labels, right? 2 for each entity type, and then another one for other. And then what we really want here is the probabilities for every label. So in order to calculate probabilities, of course, we use softmax, right? So that's pretty easy. So we use softmax right here, normalize it, and we get probabilities. And then to select the label, specific label, we can do argmax on top of the softmax probability vectors. That's it. That's very simple, and it works pretty well, I have to say. Yeah? Very simple network. You don't need any linguistic class before that, right? You don't need to know anything about the language. Yes?
What kind of activation functions are you using?
In this, what kind of activation function we're using? So this paper, if I remember, they probably used sigmoid at that time. But you could use any. Usually people use ReLU. That's the most common one. Yes.
If your country, Spain, is something long, like United States of America, with 4 words, you already have to pre-process that to know that's a unit, and then you had 2 words before and after. Right.
So the question is about what do we do with the names that have multiple words, right? You do the same, basically. So you try to predict each one of these words individually in this type of settings. What we'll get to, more sophisticated networks that will capture what you're looking for. But if you think about this, it will see here United and states right here. So this information also goes into the network. So it will help you to classify this as I-lock or something. That's the label that you're looking for the second word, right? Yes.
So in the input layer, did you say that you're just summing up all the embedding vectors for all those 6 words?
You could, but in this case, you're not summing, you just concatenate them. You put them one next to each other. So it's a fixed size, right? Because you always take 2 words before and 2 words after. And by the way, if you don't have 2 words before or after, you just put, zeros, right? You pad it.
This was before ImageNet, so it turns out, did they simply, was this convolutional? Was this a simple?
No, it's asking about, yes, asking about, it's before ImageNet, if it's similar to convolutional neural nets. No, it's actually, it's a classic feed-forward network. It's not convolutional at all, right?
Thank you.
Yes?
How large are the labeled data set sizes usually? And are those data sets always labeled by hand, or are they sometimes partially automatically generated?
So the question is about what size of label data set we use, and if we label it automatically or partially automatically. Yes. Well, it's hard to say, right? So as much as you can, just bring it on, and we train it. But I can say that these networks, they need data. They need a lot of data comparing to traditional CRFs, for example. So with CRF models or HMM models, you don't need a lot of data, right? It will react pretty fast. But here, with neural nets, since you're doing updates, you're using a very small learning rate usually, right? So your updates are very small. So you need more data in order to handle that. I don't have a specific number. I can tell you what we're doing, right? But not with this types of networks. So I'll say a few words about the size of data later. Well, actually. Okay, so we can move on, right? Before we move on, it works pretty well, but it has a limitation. The limitation, of course, you already asked about the limitation, but I'll say it. We only consider the context with only 2 words before and 2 words after, right? We can't, take into account long distance dependencies. So in order to do that, we use a more sophisticated settings. This is recurrent neural network, RNN. And here, we take this word, again in focus, this vector, we send it into this linear layer. We don't need the context vectors right now, but the output vector that will come out from here is going to be used twice. Once is this usage. We take this output vector and we send it again as input to the same linear layer, but we do this only when we want to predict the label for the next word. Okay, so it's kind of a recursive step, right? So remember that we do that word after word. We start with this word, try to predict, right? And then this word and this word. And this vector will continue to spin here, right? So we take the output, we send it back as input. Now, the operation that we do here, there are 2 vectors right here, right? So this one and this one. So the operation that we do here is just concatenation. So we put them one next to each other. So the information that flows into this linear layer contains also information that is coming from the beginning of the sentence, basically. And I will show you more about this. I'll give you a different visualization in the next slide. But the second usage for this vector is like before. It's pretty simple. So back to Spain, we take this output vector like before and we send it to another final linear layer to do the prediction. Just calculate here softmax probabilities and then argmax to pick the label with the maximum probability, and that's it. Okay, so let me give you a different visualization. So what I did here, I just unfolded this network right? Because it has this recursive step. We can unfold it. Just visualization, right? It's not really how it works. So it works like that. But this is, I can visualize it. And then you can look at the word at position t in the sentence, any position. And this is at position t minus 1, the word before, and this is t plus 1, the word after. So let me tell you what's going on here. So we take this input vector, it goes into this linear layer, simple transformation, vector transformation. And it goes here together, concatenated with this vector, which is the output vector of the previous time step. But don't get it wrong, this layer and this layer is actually the same. It has the same parameters. W1, B1, here and here. It's not a different set of parameters. And now we get an output vector right here. So first we just send it to another simple linear layer for doing the prediction. This part is also called the decoder. That's the decoder of the network. And it's doing the classification. People also call this the classifier. This is basically the classifier. And it also goes to the next time step, to the same linear layer for helping this input vector for doing the prediction. So this is how it works. And here it's very clear to see that the information flows from the beginning of the sentence throughout the entire sentence, and then every word in its turn benefits from all that information for doing the prediction. But it also modifies this vector. So this word now modifies this vector using this transformation. Now the output vector here gets modified by this input vector. That's pretty cool, right? We have information flowing from the beginning, and then we modify it and we use it to predict. So we do two things at every time step. Yes?
So like using this model, are we like assuming that the previous word is more important than the word behind it?
Yes. So the question is whether in this model, the previous word is more important than the next word, right? The word that comes after. And the question is yes, and I'll get to that, but you can clearly see here the information flows from left to right and nothing flows from right to left, right? But we will fix it very soon. Yes?
Do you cut off the number of time steps that it will be influenced by?
Oh yeah, I mean, it depends on the size of the sentence. The length.
The size of the sentence.
Yeah, exactly. So the question was about why did I break it into only 3 steps? But it's just an example. So basically, it will work the same for different sizes, different lengths, right? It doesn't depend on the length. That's what's nice about it. Yes.
So how does this work for languages which go from right to left?
So I'm a Hebrew speaker. Yeah, so the question was about languages that go from right to left. So it works the same basically, because don't get it wrong, this model doesn't understand anything about languages, right? So it's just a model, and you can just do reverse to your.
But you don't know the language is written the other way, right? So how do you decide that?
If you don't know no, you have to know that. If you don't know, that's a problem. And by the way, once we're gonna use bidirectional, I will show it. So then you don't need to know. Well, you can't always use bidirectional RNNs, right? Depends on the task. In this task, you can. Okay, now it works pretty well in sorry, yes.
I was wondering, you mentioned HMMs learn these things much quicker.
Yeah.
Flexible. So this looks like an HMM with a sort of more general middle layer. Would a Baum Welch or EM algorithm train faster than backpropagation?
I couldn't hear the last part of the question.
Would a HMM training algorithm like EM or Baum Welch,
Oh.
would it train faster than pure backpropagation?
That's a good question, but so the question was that it looks very similar to RNN, to HMM, to a hidden Markov model. So can we actually use the algorithms that we use to train HMMs for this? So remember, this is like supervised. We're aiming for supervised settings, right? With HMM, it's pretty straightforward. So you just collect probabilities, but maybe you're referring more to like CRF and more fancier models, HMM models, where you take actually feature functions, and then what you use there is actually gradient descent, also for CRF, right? It's a type of gradient descent, which is basically what we're doing here. But here it's more general. So you need to account for more information, not specific feature functions. So basically, in theory, the information here is endless. So you need to take that into consideration somehow. Yes?
Can you also feed in not just word features, but some metadata type of features into this network along with the word features?
Yeah, so the question is about whether we can use some metadata information and push it into the network. The answer is yes. We do that. We use different types of metadata into the networks. There are different works on that. Yeah.
I have another question.
Sure.
You can also have like sequential metadata, but what about, can you also merge in like static type of metadata along with the sequential?
Yes. Yes.
How would you bridge the gap between the?
It really depends. So the question is about, can we model some or use some data that doesn't have this sequential feature, right? Together with the sequential data. So it depends on what data do you want to use. Like for example, the domain of the text, right? Sometimes you have different domains, like financial data and legal data and different types of, so you can model that and put another vector basically for every word, and it will look the same for every word, something like that. So there are different techniques. There's all techniques that you can try and tweak the network to work. Okay, so it works well, but what I was about to say, that it works well in theory. It doesn't work well in practice because the main reason is that how we actually train this network, right? So we train it with backpropagation, and backpropagation is not exact science, right? It's actually a heuristic. It's something that doesn't do exactly what we want, and we try to update those weights somehow. But for these types of networks, there are many layers. Basically, it's a very deep network. Basically, the same layer, but it works like as if it was a very deep network. The problem is that it turns out, using backpropagation, is that sometimes this vector gets very quickly overwhelmed by the large amount of information that we put on this vector, and sometimes the opposite. We don't have any information to contribute because it doesn't pass the kind of, the level of importance threshold or something like that. So I'm trying to give you intuition for two mathematical problems. One is called vanishing gradient problem, and the other one is the exploding gradient problems, right? But I won't go into the mathematical details. It's evening now. So we just gave you the intuition, but you can go and look for these online. And there are different ways to handle these problems. One of them is to use a specific flavor of RNN. This is long short-term memory, or LSTM. It's very popular these days. And it looks the same, but instead of using this linear layer here, it uses more complicated transformation, right? It has multiple linear layers inside, gates, different calculations there, but essentially it works the same in terms of input-output, right? I won't go into the details like inside LSTM cell, right? But you can get the details online. Probably some of you are familiar with all that. Now, I will say one thing about this. What it intuitively adds is that it's not just remembering information. It also provides some tools for the network to be able to forget some of the information when it's not needed anymore. So it has a control mechanism there. When do you want to remember something? When do you want to forget? So it provides those tools to the network, and the network kind of can push some buttons automatically where it needs something and where it doesn't need that. So it forgets and make room for more important information. It's all intuition, right? So you can, mathematically you can see that too. Okay, so LSTM this is what we're doing for named entity recognition. So we get, we have this text, we break it into words, every word gets into LSTM, information flows from the beginning of the sentence, and then we said that we're missing the information that comes from the right side of the sentence, then we do this. So we add another process that goes from right to left. Now we have two processes, right? One that goes from left to right, one goes from right to left. And now those are independent processes. So now at every time step, we have two output vectors. And we typically take them and we aggregate them somehow. We can average those vectors. We can put them one next to each other. That's what we typically do. We concatenate them. And then we set this double-sized vector into the decoder, the last part, right? This linear layer for doing the classification and argmax, and that's it. All right, so that's a bidirectional LSTM for sequence labeling, specifically for named entity recognition, what you see here. That's very effective. It works pretty well. And now we're going to add some more fancy features to this network. But first, you can take this vector here, and instead of send it to this output layer to do the prediction, you can set it to another bi-LSTM layer and another one, right, if you want. As many as you like. So this is like a big monster of many bidirectional LSTMs. You get many parameters, and it's becoming very, very deep, right? And it turns out to handle better patterns in your data in a way, but it also may overfit your training data. So you need to use more complicated tools to do regularization and things like that. Yes?
Is it like a hidden Markov model with more layers of hidden states?
If it's like hidden Markov model with more states.
More hidden layers.
Yeah, more hidden layers, right.
Instead of one hidden layer.
Yes, in a way, yes, I guess. But it has much more parameters, I guess. Yeah.
So did you say there are two concatenated layers in that bidirectional LSTM? Essentially, there are two columns, two vectors.
Yes, so the question if we have like two vectors that come out of a single LSTM layer. Yeah, one for each direction, right? So you can see this one vector here, and this vector also goes here, and you concatenate them. Now you have one. Okay?
It's just to make sure, I'm sorry, Greg.
Go ahead, you start.
Just to make sure I understand this.
Sure.
In essence, if you've got a sentence, pretty much again, you sort of read it from the front to the back to this point, and you go on and read it from the back to the front to this point, and then based on the aggregation of information from both of those things, that goes out and points out to your current point in the classification. Is that the right way to read this?
Yes, exactly. So the question or the clarification comment here is the way to read this. It's a bit complicated, right? So if we want this is your classifier, right? So we're going to do the classification from left to right. So we start here, want to classify this word, basically. So we need this vector to go here, right? So you need to start from the end, and you will see how things are connected. So you want to, PyTorch or TensorFlow computational graph is calculated, basically. So you start from the end here, and you see how things got connected, got calculated, right? So here you get this vector right here that goes into this final layer, and you see, it's composed of these two vectors. How do I get this vector? Okay, to get this vector, I need to get this vector. In order to get this vector, I need to get this vector, and so on, right? And it'll go all the way here. And so that's how you do it. So you need to calculate everything, but if you open this as a graph, you'll see that it's solvable. So, yeah. Yes?
In some image recognition models, they have residual layers.
Yes.
Is this the additional layers here fixing errors from the earlier stages? Is it something like a residual net?
Yeah, so the question is about whether it's similar to residual nets and for image recognition. So there are works that do this, take this vector and do this transition too. So add this vector right here to this vector, so do like a residual step. But remember that LSTM inside does something that's very similar to residual net. So it has some, residual kind of steps. If you're familiar with the inside, yes.
What is the residual step being done?
Residual step is like if you take vector here and it goes into this component and you get a vector output vector right here. So instead of using this output vector, you take the input vector and you aggregate it with the output vector. So basically your neural net layer just adds information to the input vector and not replaces that information, if you like. That's the intuition. Yes?
Does the arrow going up into the LSTM also go into the one above it?
So the question is,
So you see how you have an arrow going into the bottom LSTM? Does that same arrow go into the one right above it?
your word is error, you said?
Arrow.
Yeah, error.
He's asking if basically your picture is mislabeled. He's asking, those two LSTMs that are close to each other, is there in fact an arrow that joins them together? That's his question.
No, yeah, like these two?
Or the arrow going in the bottom one, does that same arrow also go in the one right above it?
So yeah, his question is like, does the when embedding the Washington get inputs at each?
Oh, I see. Yes, yes, sure. So there is such error that goes like that. Yes. Yeah. I didn't put it too many arrows, so yeah. Okay, but not here. So here, yes, this one also goes right here. Okay, yeah, but not the embeddings from here. Yeah. Okay. So yes.
So when you're saying concatenating, it's basically you are deciding how much before is important versus how much the later part is important, right?
Yes.
So it's not just a concatenation. You have to kind of weight it in certain way.
You're asking about disconcatenation, for example?
The forward and the back.
Oh, yes, disconcatenation is the forward. So the question is about, about concatenation forward and backward information. So yeah, we just concatenate. That's the the most common technique. But you're asking about specific.
It's like, isn't the relative importance of the two things? So it's not just a plain concatenation.
Interesting.
It depends on how long the sentence is and where you are. You may have 3 words to the left of it and 50 words to the right of it.
Right. So if you have more words in this part, so this vector will have more information, and from what we saw in the research community, this vector will contain more information from these words, the words that was the last words that we processed. So you're kind of missing some level of the information that happened before. That's natural in these types of networks. Yes. But it's okay too, right? Because most of the information exists in the near environment, right? So this is why HMM is doing well, relatively well, right? So with these networks, you can improve, but with a few more points.
If the correlated words are far apart, you will actually miss that.
Right. So, but for this specific task, for named entity recognition, most of the information is local. There are some information that it's not. It's pretty far, but not most of it.
I just want a couple of points to bring up. One is this obviously isn't going to work for speech recognition because you can't go on and go all the way.
Exactly.
Second point is that the context is probably, I guess, limited by a period. You could say, for example,
Yes.
some people might say that Trump is intelligent. They would be wrong. Well, it turns out you sit there and then do the stuff there, then you have more context off to the right, but you were limited by the period.
Exactly. So there are two very important comments, right? So one about the size of the sentence. We typically work on the sentence level, not more than that. So as we break text into words, we also break it first into sentences. Okay, so that's another task. We do that. We work on the sentence level. And what was the other comment?
You can avoid garden path by going backwards, but this is obviously not for speech recognition.
Right, yeah. So we said that in the beginning, right? So the bidirectional LSTM doesn't work for every problem. It works for problems that we can actually have all that information, the input of the entire thing. So for information that comes, token after token, we can do that. Like speech recognition, so we can only do unidirectional LSTM. Yes, of course. also for language modeling, for predicting text, right? So for trying to write a comment automatically or something like that. Yeah?
How do we address things like emojis in sentences, or sometimes we use like jokes or sarcasm, puns? How can that play out when you have this multi-level LSTM?
I mean, if I understood the question, so how can we take into account sarcasm or emojis, things with some level of sentiment, right? That's the...
Or sometimes we have like different languages. For instance, like if we say English, we can go from left to right, and sometimes we may have English and Arabic or English and Hebrew mixed together.
Oh, yeah.
How can we...
Yeah, so yeah, more questions about more challenges in languages, right? So when you have multiple language inside a text, yeah, so it's all solvable in a way using some, specific techniques. So for example, for breaking, first we're looking for, we have preprocessors that try to detect language, right? Detect the language and the span of the languages, like to do what we call code switching, to find where the language transit. Arabic and English is pretty easy, right, to detect because they use different scripts. But English and French, it's a bit more complicated. And we try to do that and then take the English part and send it into like a model that was trained on English data and the French sentence into, or the French segment into a model that was trained on French. So there are different techniques to do that. For emojis, we just treat it as another token. So emoji basically is text, right? So we do that. And we don't take into account anything other than that, any other information, sarcasm, sentiment, whatever you think about the text and all the semantics that you can think about, we don't extract it manually. We don't model this thing manually, we just model the words with embeddings. So we're hoping that all that information, is in the embeddings. That's what we hope. That's what's nice about this model. But then, you get a model that's very hard to interpret. And I want to get to that and show you some things that we did with interpretation. Okay, so now let's talk about two more things about this network. One is the decoder part right here. So we say that we start, we just do this. We take this probability vector and we just pick the one with the, the maximum probability, right? We do argmax on this. That's very simple. But then we come here, and when we want to predict the label of this word, we don't take into account the label that was predicted here. We do this independently, right? And that seems wrong because there are some, very specific rules that we want to follow. For example, the label I pair can only happen after B pair, right? That's basic, that's by definition. And we don't enforce this rule here. So in order to enforce those rules, we use a different decoding technique. Instead of predicting every label individually, we try to predict the whole sequence together. So we're using CRF, conditional random fields. Basically, it's just HMM. But we call it CRF because it's a much more generic and nice model. Anyway, so we try to predict everything together. We'll look at these probability vectors. We still calculate them, but instead of picking the one with maximum probability here, we look also at the probabilities of moving from one label to another, right? So we consider that. We also take that into consideration, and we try to calculate a score for the whole sequence. So the score looks something like that. A score for a sequence of labels. That's a specific sequence of label. So Y1 to YM for an M word sentence, right? So the score looks something like that. It has two main components. Sometimes we even add more, but those two main components, the first one is just the sum of all the probabilities of every label, right? So Y1 is the label and ST is the vector, the probability vector at time t, right? So this is just the specific probability of this specific label. So we sum them up, right? That it looks like what we did before, basically. But then we add this. So this component is the sum of all the transition probabilities for moving from yt to yt plus 1, right? So this matrix of probabilities, we hope that it will do something like that. It will give lower probability to transitions like from O to I pair, which doesn't seem right. Then probability for moving from B pair to I pair. And that's easy to calculate because we have all that information, right, in the training data. We have all these transition probabilities, yes?
I think those are probably the log probabilities, though, prior to the softmax, right?
Yes. So the log probability.
S and T.
Yeah, so you can calculate log probabilities, instead of doing because it's additions, you're right. So you're using log probabilities here instead of probabilities. Yeah, sorry, I didn't get into everything, accurate because I wanted to give you the intuition more. But yeah, definitely, it's log probabilities. Okay, so we get this, and then in order to decode with this model, to find the best sequence, you just do this, right? Argmax over the whole possible set, the set of all possible sequences, label sequences, but that's a lot, right? So don't do it, using a brute force algorithm. You can use Viterbi, right? Like a dynamic programming algorithm, something like that to do that. And it works pretty well. It improves results by a few points using this. But it also adds more complication to the model, right? So prediction takes more time now, obviously. So, Viterbi is O n to the third or something, right? So it adds more complexity. Yes? Sorry, I didn't hear. Yes. So the question is whether we learn those probabilities, right? The T matrix. So yeah, you can learn them directly from the data set, right? You can do as simple as maximum likelihood, right? Expectation or something. Yes. You typically learn this together with the same training procedure. Yes. You do everything the same time. So yeah, you can correct the model based on the CRF results. That's what you do, basically, right? The backpropagation works with the results, yes. Okay, and then you have another thing that we're doing is character encoding, and we mentioned this before. So we break the text into words, we said before, and then we use the individual vectors, right, embeddings. But what if we don't have those vectors for particular words? And those are the vocabulary words, and they turn out to be names actually, right? So that's important to us in this case. And even if we do have vectors for all the words, we still want to capture some morphological features of those words. Like for example, in English, capital letters are a strong indicator for a name, right? So we want to capture that. And there are other such features in other languages. Like in Hebrew, for example, the definite article is attached to the word. It's not like in English. And then for proper nouns, for names, we don't use that. We can't, define proper names like that. So it's another morphological feature that we want to capture. And there's some other in other languages. So in order to do that, we use another BiLSTM that works on the character level. And now we push characters into another, BiLSTM process, but we don't really need the output vector that goes, out of this LSTM node. Because we're not doing any prediction with this vector, right? So we just pass it on to the next step, right? Next character. Next character modifies this vector and goes on. And eventually we take this output vector, hoping that it carries information from the beginning of the word, information about all the characters somehow. So we have two vectors, one that goes out from the right side and one that goes out from the left side. We concatenate them together with the third vector, which is the word vector that we already have. So this representation is what we use to represent a word in these settings.
I can really understand going backwards in sentences and forwards. Could you give me some intuition But going backwards and forwards with words at the character level?
Yes.
Is there language independence benefits?
For characters, you mean? Yeah, maybe. So the question is about why go back and go in two directions, basically, on the character level, right? So, also for language independence, right? So this is how you can capture like the two languages that goes from right to left or left to right, but not only that. So remember that we said that before. So this process doesn't really, it's not that this vector right here will contain all the information of the characters at the same level of information. So this vector will mostly contain information from the last characters here. And this vector will mostly contain information from the last part of the word. So basically this way you capture prefixes and suffixes. And for some languages it's very important. Like Hebrew we have prefixes and suffixes, right? In English you only have suffixes basically. So it's different. Yes?
So why not use a convolutional network and just hiding it to a fixed length?
Right, so why not using convolutional neural nets? So first, yeah, sure, why not? I mean, we can use convolutional nets. We're doing that too. Convolutional nets, so people try to do convolutional nets right here and to do that, and I will show that in the next slide, I think. Which, it's hard to say. I can say that the convolutional net is faster, so, those very small points. So if you need a fast model, use convolutional nets. Yeah, definitely. Remember, this adds much more parameters to the model. It's another LSTM with all the different matrices inside the LSTM. So it's a lot. Yes?
If a word is misspelled, does the character embedding take care of that, in addition to the word embedding?
Yes, exactly. The question is about if we're misspelling some words, right? So the character-based encoding here takes that into account because if we didn't get the word right and we don't have the vector for that word, so at least we can capture some features of that word, right? So if it ends in a way that usually names end, or it ends in a way that usually a word that are not names end, right? So we can capture that. So it's a kind of a fallback model. Yeah, it works well for out of vocabulary words, but not only that, it also, if you do have the vector of a specific word, it still doesn't capture the fact that it was mentioned with a capital letter, right? So that will add you a lot of information. How much? Take a look here. So we did this experiment. We trained a BiLSTM model that works on the word level, and then we added this character-based level model. You can see it here, and we trained it for English, Arabic, Korean, some other languages. I just put those three. Each one of them introduce, different challenges. I don't know if anyone here speak one of the other two languages, but they have, other challenges than English, and you can see that it's better, across the board. This is all F scores, okay? Yeah. How do you find what? Sorry?
For example, for language like Chinese, how do you find the character level?
How we find the character level vectors, you mean? How we encode the characters, basically? We just break it into characters, right? We break the text into characters, Unicode characters, and we follow that.
So you can also use stroke engrams or different strokes.
Oh yes, you can do that. But I have to say I'm not Chinese expert at all, but yeah, we can essentially can do that, right? So you can break it into some level of characters. Yes?
Do you have explanation why the same model works particularly well in Korean language compared to the other languages?
It's a very good question. So the question is about why we got a nice boost Korean comparing to the other. So one reason is that we have less data for Korean.
The corpus is 4 words.
No, not 4. But we have a little bit less than that. So maybe with character encoding, it was good enough, so you don't need a lot of data. It learns also from some of those things. And I think also Korean, I'm not a Korean speaker, do you know Korean? So Korean has all these postposition clitics that get attached to the words, like josa or right things like I'm not a Korean speaker, but I know from all the problems that we're seeing, and we have Korean speakers, and those are very critical, right? So it probably helps. Do you want to add something
Yes,
to
that's
this?
exactly correct. Yeah.
Oh, okay.
The characters are made of characters too. Actually, like
It's a very unique language. Yes. Yeah.
Something else along those lines. My understanding is Korean is a written language is relatively new.
yes.
Yes, it is. True.
So when they defined it, it hasn't had a whole lot of time to spread out and not be consistent. How the characters and how the words are spelled and the like.
Yeah. So the comment.
It's been around a long time. The Arabic's been around a long time.
Right. The comment is about that Korean is a new language. Okay.
In the written
Yeah, the written mechanism, it's a new thing, relatively, right? Comparing to Arabic, so it's still not consistent. That's what it is.
The thing is more consistent.
It's more consistent, yeah. Then.
A chance to diverge as English has all this French and all the other stuff.
Right. So we have
Korean doesn't have that much of a problem with it.
Cool. Okay. Yes.
So have you done any character-based by LSTM, not like word-based embeddings? Don't use word-based embeddings, just use the character embeddings, and then do the same by LSTM. Then what would the results like?
So you're asking whether we used just characters?
Just characters.
Yes, we did that.
Okay.
Results are not so good,
Oh.
but not so bad too, but less than what you see here. It's very interesting for us to use only character-based models. That will make our life much more easier, but it doesn't work as good.
How far they are from these numbers?
Yeah, so like around 70 something. Okay, yes?
I was just wondering, like, did you try the traditional machine learning approaches, like sequence learning, like, I don't know, CRF or something, and how much different is it from, like, these results? Like, is it
So yeah, so the question is whether we compare these results with traditional models, and the answer is yes, and in 2 slides I will show it. Okay, so let me conclude this part of the session. I have some more. I hope that you're not so tired. Anyway, so to conclude this part, I don't have a lot more. So to conclude this part, we have so far 3 main components. One is character encoding, word encoding, and then we have decoding, right? So character encoding, or I'll say that people use different technologies, referring to different questions that I got. Like if you look at this table that I took from this paper, so it kind of summarizes the different technologies that people, different technology combinations that people use for the different components. Like for example, if you look here, Lempel and others from 2016, they use LSTM for character encoding, LSTM for word encoding. By the way, it's by LSTM. And then CRF for decoding. That's exactly what I showed you, right? But there are different techniques here: CNNs, dilated CNNs, and LSTM for doing the decoding and things like that. So it's an active research area, and there are many works published. And very interesting. Now the results that I want to show here. So we compared, a deep learning model that we trained, like I showed you here, but a few more tweaks, a few more things that we tried here, and we compared it with our traditional model that we're using for many years at Basis before I joined Basis, and our clients use the same model, and you can see that without knowing anything about these languages, I don't nothing, no linguistics and nothing, and here now linguists work on this, and you see that results are better, right, across the board. Now it doesn't come for free because those models are much slower in prediction, right, and that's a big hit. So we need to handle that, and we're doing that, but that's a different topic, maybe for another session or something. Yes.
I have documents maybe? And second, like for the evaluation test, what kind of
a combination. You can look at it, but it will take, it will give you some reward for partial matches, not complete reward. Yeah. Yes.
How do these numbers compare to human performance? And do you think
Human performance?
Yeah, and do you think we're far off from surpassing that?
That's a good question. A question is about comparing to human performance. So I can say this. One of the most difficult problems of named entity recognition is not what we're doing here. It's actually getting people to agree on the guidelines when they do the annotation, right? So agreement is not that high at the beginning, but once we actually teach the people, right, and work with them and write down everything, it turns out to be something that we can handle. And the agreement score, kappa value, gets higher to the point where the data is usable, okay? So based on that, I can only say that human can do better than this, right? But I can't measure that. Yes?
So in this, you had around like 7 or 8 categories of entities, right?
So yeah, specifically here, the question is about how many categories we use, how many entity types. Specifically here, we use PLO, three types. But we have more. Here, we just evaluated on those 3.
My question is that, like, if you have, like, let's say, first question is like how many actual labeled examples per category you had, like, if you can give like approximate number. And let's say you add like 10 more categories, would your accuracy go down? And also, like, how many samples would you need for a new category to be added? Like, let's say I want to add a category called animal type. So how many more examples would you need to give in the same accuracy?
So yeah, so the question is about numbers of examples that we need in the data set for different types of entities, or if we want to add more entity types, how many examples we need. It's really hard to answer those kind of questions, and I know they're important, but so as much as you can, I guess, again, like we said before, but for these types of networks, you need relatively, many examples. I don't know how to pick a number here, but you need like, thousands of mentions or something like that. But it's very difficult to define it. I can specifically here, we're using corpora of about 300,000 words, so per language. That's what we have. Yes?
I just wanted to follow up on the Twitter. Did you do this specifically with Twitter data? The language there is kind of degraded over regular, and what were your results if you did?
So the question is about if we did this on Twitter data, and Twitter data doesn't use like an official way of expression, and if results are worse than applied on official language. Yes, so we use Twitter only for some languages, not, so we tried on Arabic, on English. maybe a few others. But so yeah, the results on Twitter data is not that good comparing to the official language. Because there's some noise there, as you mentioned. But if you annotate more data, it gets better. So that's one thing that is encouraging here. So yeah, you can model that information, but you need to annotate more data. Yes. Okay, so let me take you to the fun part now, right? As always, a model. We had to wire things, and it's pretty cool. And now let me talk about what this network actually learned, and that's tricky. And I'm going to show you just a few things. Now, the main thing here is that this network is pretty difficult to understand, right? And I saw people citing this article written by this famous oncologist, Dr. Siddhartha Mukherjee is an oncologist, and he wrote this article in the New York Times Magazine a year and a half ago about an experiment that they've been doing in their hospital. They're trying a deep learning based algorithm for predicting death of oncological patients, and while the algorithm worked pretty well in terms of accuracy, better than the doctors in the department, but they couldn't understand what the algorithm is doing, right? So for them, it's kind of illegal to use that, because they can't just sit in front of oncological patient and tell them that they have a few months to live, and it's just because the algorithm said so, right? So and he said the algorithm looks vacantly at us when we ask why. It is like death, another black box. So people call this problem the black box problem of deep learning, of NLP, and it's a very active research area. People are working in this field. There are different workshops, black box NLP, black box image recognition, and things like that. So the main problem, I think, is, with traditional machine learning, we manually create all these features, right? And we push them into a complicated model, whatever, but then we can measure importance of the specific features. Depends on which model we're using. With XGBoost or anything like that, well, tree-based algorithms, we can kind of measure the importance of all these features. But with deep learning, we don't know what the features mean, right? We don't know anything about them because they were created automatically by the network during training time. So we don't know anything about that. So at Basis, we're doing some research in this direction. We're trying to understand that. So if we look at this network, right, the same thing that I showed you before, it's a bidirectional LSTM. Very simple one, no character encoding, nothing like that. So we said here, with the simple version of this network, that we use argmax here to find the label of this word. Now, as I said before, you can look at this step as the classifier part of the network, and you can look at this, the encoder, as kind of a feature generator, right? That's a feature, something that generates features. Basically, this is the feature vector that represents this input right here. Okay, so those features are created automatically. So we want to look at these features. So basically, let's look at this vector, but let's look at just half of it, which is the vector that goes in one direction, just in one direction. Let's look at this vector, right, with all its 500 dimensions. I say 500, but it's actually a hyperparameter to the model. You decide what the size of this output vector, right, the size of this particular vector. So let's say it's 500. That's what we're using at Basis. So we have 500 dimensions right here, and we can look at this vector while it moves from one word to another. It travels in time, right? And we can see how it gets modified and see if we detect specific patterns. So for that, we created this tool, simple tool. It works on top of a model that we already trained, and then you can insert a sentence here and get the predictions back from the network. So you can see here the specific word, individual word that the model So we're using a tokenizer before. And then you see here the labels that were assigned by the model. So in this case, all words got O, right? Correctly. I don't see any names here. Now what you see here, that's the fun part. So this is that vector that I told you about in one direction. So if you scroll down, you'll see 500 rows here, okay? And each row here, we call it also a neuron, right? That's a feature, a neuron, dimension, whatever you want to call it. So every word here represents a specific dimension of this vector. And you can see the numbers are changing from word to word. Now the numbers are between -1 and 1. Just because the last step of LSTM is tanh, right? So it squashes the data between -1 and 1. And we put some colors here just to make it easier for us to read. So with -1 is dark blue and +1 is dark red, and everything else in between, like green, is around 0. So then you can insert here a sentence and look at specific pattern. I see a pattern here. So number 9, right? So I can look, it gets negative right here, and it remains negative, strongly negative, and at some point it gets back to normal, and then negative again. And you can see that the word your is here and here. Maybe it relates to that. It's difficult to interpret. Those are the features that the network actually created, right, for doing the prediction. But it's not interpretable, right? So how can I be sure that this feature is actually doing something with the word your? So I can add more sentences, right, with your, and more and more and more sentences, and eyeball the results. Crazy idea, right? But we did it. So we tried many sentences with all, and spent a few nights with many cups of coffee and beers, and eventually we find some interesting patterns. So let me show you just a couple of them. First pattern. This one, neuron 280, gets a relatively positive value when it sees punctuation marks, for example, right, like this. You can see here, and if you run many sentences, it will do the same. Now, it's not exact science, okay? Sometimes there are some insignificant changes, right, that we cannot explain. But in most cases, that's what it does. But you can also see another pattern, interesting pattern here. I mean, this information is not remembered for too many time steps. So it gets positive and immediately here gets back to normal. Here a little bit more, but not more than 1, 2, 3 time steps. We remember this information. So it means that probably for named entity recognition, punctuation marks are important, but we don't need to remember them for too many time steps. Let me show you another neuron. This one, 189, gets negative when it sees the word in, which might be a strong indicator for a location, right? So look at this sentence, I live in New York, right? So the system, the model could assign the correct labels here. GPE is just a location, basically. It's a geopolitical entity, okay? It's a location that could be also organization. So you can see that capture it correctly, but if you look here, I live in a van, right? So that's not a named entity. And the system was able to correctly detect that, but the neuron still did the same, right? So the network, the classifier on top, uses many features, many neurons, not just this one, right? So that's pretty cool. We can see that how it's actually working. Now check out this sentence, I live in a van and I have a new guitar. So here you can see how this neuron is working, right? So this neuron gets negative right here, and it get negative, it remains negative, and a few, but it's 5.5 time steps, it gets back to normal. So we need that information. We need to remember that for a few time steps until we decide to drop it. Yes?
What happens if the van is capitalized?
Yeah, so the question is about if one of the words is capitalized accidentally. Yeah, so the model will be sensitive to this. So if you trained on official language where only the things that need to be capitalized are capitalized, so it will probably make a mistake.
How is it not just picking up entities but from the first capital letters?
From the first what?
Capitalized words. As just, this is a simple model as just first letter capitalized words.
So it doesn't capture just capitalized words because it sees capitalized words that are not names.
Outside of the end of the beginning.
Yes, exactly. Yeah.
I just wanted to ask, so when we pass in these vectors in our LSTM cells and we do a concatenation, do you add those numbers up or do you...
No, just put them one next to each other. We extend the vector.
Okay.
The question was about how we concatenate, basically. Concatenate is just putting one next to each other, not adding anything.
So you pass it in together one.
Exactly. Okay. So there is another question there.
So my question is, when you train the same model with different render initialization, will the result be the same?
Say again, sorry.
Train the same model but with different render initialization. Will the same result be the same?
So the question is about if we initialize the model again and retrain it again, you might get different results, but slightly different. But in order to evaluate, and that's what we did there, you run the model a few times and then you average. That's what we did there to get real evaluation results. Yeah. So how much time do I have?
About 10 minutes.
10 minutes, so yeah. So I just have a few more slides to tell you about transfer learning and that's it, okay? So it will take less than 10 minutes, yes. Yeah, let me say a few words about that too, maybe, during the last part. Anyway, so that's about this, and the next thing I wanted to share with you, that will be the last thing here in this presentation. It's about contextualized embeddings or transfer learning. That's one of the most popular topics these days in NLP. So, words might have different meanings, right? You know that. So here, right, in this thing, call has at least two meanings, right? And these two meanings. One is to call someone a name, right? Like to assign a name, and the other meaning is to call someone on the phone, right? There are many other, probably other meanings too. Now, if you take we said that we represent words with vectors, with those static vectors that we create, just one vector per word. But a word we just said might have more than one meaning, right? So how can we take that into consideration? Because when we insert the sentence into a NER model, we have the context, right? We put a whole sentence. So we have the context, we can decide on the specific sense, on the specific meaning. So we don't want to use only like static embeddings, right? And by the way, I took the vector of call from Word2Vec Google News collection. You can get it online, all the vectors trained on news. And so I took the vector of call, I calculate cosine similarity of call and the vector of the word name, if you want, representing this sense. And also the same thing with the word phone. And you see the results here, right? So it means that call has more of the first sense in it, if you like. Anyway, so we really want something else. We want a contextualized embeddings model, a device that will generate specific vectors based on the surrounding context, right? When we assign the word to the network. So if we have this sentence going into the named entity recognition model, I have a call with them later in the afternoon, we're going to create this vector, and if we have this is our initial call for speakers. That's a different meaning for the word call, so we want to use a different vector. So in order to do that, to build these contextualized embeddings, we can try to build some models and not just like a repository of vectors. We want to build a model, pre-train it, and plug it into the network. So there are many works in this field, as you're probably familiar with all these names: BERT, Elmo, GPT, GPT-2, XLNet that was recently released. So very interesting works. I don't have time to get into all the details. Let me show you two quick examples. One is this work by Google from 2015, semi-supervised sequence learning. They did a very simple thing, but very efficient. So they trained a language model using unidirectional LSTM. So language model is exactly like what we did, but only unidirectional. And we're not trying to predict here NER labels. We're trying to predict the next word in the sentence, right? So I will call you, that's the sentence, as you can see. So given I want to predict will, which is the next word. Given will, predict call, and so on. So the number of labels here is huge, right? Like, let's say, 500,000 words in your vocabulary, something like that. Okay, and to train this, you just need a large collection of text, right? For free, you can get it. No labels are needed. So you train that as much as you want, as long as you want, you end. And then you go here to this step. Now you want to train your model for named entity recognition with your supervised data. So the only thing that you do, different than what I did before, we initialize these parameters here with the parameters that we ended up here. So we take all these parameters, we plug them into this network, and we start from this point. Now we have a lot of information about sequences of words. So in a way, we for the word love, right? So we know to predict what will be the next word, not just by seeing love, by seeing all the words before, right? So we know what to predict next. By knowing what to predict next, that's output vector right here, which will go out from here. It has information about the word love, right? That's a modified version of the embedding vector. So that's actually what we wanted, basically. And we keep training these parameters. So this model will start as a language model, but with our labels for named entity recognition, we'll modify it, right, to adjust, and we tune it to work better on named entity recognition. And that works pretty well. My last slide is this. So this is another example from 2 years ago by Salesforce. It's called COV. And this is the same thing, but instead of doing language modeling, they did machine translation models. So they use sequence to sequence models. And they just plug, the numbers that they plugged in here are the parameters of the encoder. So they use LSTM plus attention. I won't go into the details. You can go and look for that. I just want to show you how creative people get when it comes to doing transfer learning. That's pretty cool. That's one of the most important topics these days, because you can get better results by using data, unlabeled data, right? So that's pretty cool. So all state-of-the-art results are now using all these transfer learning techniques across the board, all different NLP tasks. With that, I will stop. Thank you so much for coming, and happy to take questions if you want.
Question.
Yes.
How does it behave for the Western languages with more structure? So Eastern languages where the nouns have declined, for example. The words can come anywhere because of the question.
So the question is about what's the difference between?
Right. What's the behavior of this mark? Languages, difference in behavior.
So what's nice about this model, it doesn't understand anything about the language itself. So as long as the information is encoded sequentially, right, it will capture that information in a way. That's what I'm thinking here. It doesn't get anything about the language, right? It doesn't matter. But as long as you can get the information sequentially, and it happens also maybe in every language that I know. So.
For German, the verb comes at the end.
You're right, but it will learn that, right, for German, because you have training data. So it will learn that essentially, right? The training data will look like that.